Chapter 4 Aerodynamic Factors. Introduction. Several factors affect aircraft performance, including the atmosphere, aerodynamics, and aircraft icing. Pilots need an understanding of these factors for a sound basis for prediction of aircraft response to control inputs, especially with regard to instrument approaches, while holding, and when operating at reduced airspeed in instrument meteorological conditions, IMC. Although these factors are important to the pilot flying visual flight rules, VFR, they must be even more thoroughly understood by the pilot operating under instrument flight rules, IFR. Instrument pilots rely strictly on instrument indications to precisely control the aircraft, therefore, they must have a solid understanding of basic aerodynamic principles in order to make accurate judgments regarding aircraft control inputs. End of page 4-1. The wing. To understand aerodynamic forces, a pilot needs to understand basic terminology associated with airfoils. Figure 4.1 illustrates a typical airfoil. The chord line is the straight line intersecting the leading and trailing edges of the airfoil, and the term chord refers to the chord line longitudinal length as viewed from the side. The mean camber is a line located halfway between the upper and lower surfaces. Viewing the wing edgewise, the mean camber connects with the chord line at each end. The mean camber is important because it assists in determining aerodynamic qualities of an airfoil. The measurement of the maximum camber, inclusive of both the displacement of the mean camber line and its linear measurement from the end of the chord line, provide properties useful in evaluating airfoils. Review of basic aerodynamics. The instrument pilot must understand the relationship and differences between several factors that affect the performance of an aircraft in flight. Also, it is crucial to understand how the aircraft reacts to various control and power changes, because the environment in which instrument pilots fly has inherent hazards not found in visual flying. The basis for this understanding is found in the four forces acting on an aircraft and Newton's three laws of motion. Relative wind is the direction of the airflow with respect to an airfoil. Angle of attack, AOA, is the acute angle measured between the relative wind, or flight path, and the chord of the airfoil. Figure 4.2 flight path is the course or track along which the aircraft is flying or is intended to be flown. The four forces. The four basic forces, figure 4.3, acting upon an aircraft in flight are lift, weight, thrust, and drag. Lift. Lift is a component of the total aerodynamic force on an airfoil and acts perpendicular to the relative wind. Relative wind is the direction of the airflow with respect to an airfoil. This force acts straight up from the average, called mean, center of pressure, CP, which is called the center of lift. It should be noted that it is a point along the chord line of an airfoil through which all aerodynamic forces are considered to act. The magnitude of lift varies proportionally with speed, air density, shape and size of the airfoil, and AOA. During straight and level flight, lift and weight are equal. End of page 4-2. Weight. Weight is the force exerted by an aircraft from the pull of gravity. It acts on an aircraft through its center of gravity, CG, and is straight down. This should not be confused with the center of lift, which can be significantly different from the CG. As an aircraft is descending, weight is greater than lift. Thrust. Thrust is the forward force produced by the powerplant/propeller or rotor. It opposes or overcomes the force of drag. As a general rule, it acts parallel to the longitudinal axis. Drag. Drag is the net aerodynamic force parallel to the relative wind and is generally a sum of two components, induced drag and parasite drag. Induced drag. Induced drag is caused from the creation of lift and increases with AOA. Therefore, if the wing is not producing lift, induced drag is zero. Conversely, induced drag decreases with airspeed. Parasite drag. Parasite drag is all drag not caused from the production of lift. Parasite drag is created by displacement of air by the aircraft, turbulence generated by the airfoil, and the hindrance of airflow as it passes over the surface of the aircraft or components. All of these forces create drag not from the production of lift but the movement of an object through an air mass. Parasite drag increases with speed and includes skin friction drag, interference drag, and form drag. Skin friction drag. Covering the entire wetted surface of the aircraft is a thin layer of air called a boundary layer. The air molecules on the surface have zero velocity in relation to the surface. However, the layer just above moves over the stagnant molecules below because it is pulled along by a third layer close to the free stream of air. The velocities of the layers increase as the distance from the surface increases until free stream velocity is reached, but all are affected by the free stream. The distance, total, between the skin surface and where free stream velocity is reached is called the boundary layer. At subsonic levels, the cumulative layers are about the thickness of a playing card, yet their motion sliding over one another creates a drag force. This force retards motion due to the viscosity of the air and is called skin friction drag. Because skin friction drag is related to a large surface area, its effect on smaller aircraft is small versus large transport aircraft where skin friction drag may be considerable. Interference drag. Interference drag is generated by the collision of airstreams creating eddy currents, turbulence, or restrictions to smooth flow. For instance, the airflow around a fuselage and around the wing meet at some point, usually near the wing's root. These airflows interfere with each other, causing a greater drag than the individual values. This is often the case when external items are placed on an aircraft. That is, the drag of each item individually, added to that of the aircraft, are less than that of the two items when allowed to interfere with one another. End of page 4-3. Form drag. Form drag is the drag created because of the shape of a component or the aircraft. If one were to place a circular disc in an airstream, the pressure on both the top and bottom would be equal. However, the airflow starts to break down as the air flows around the back of the disc. This creates turbulence and hence a lower pressure results. Because the total pressure is affected by this reduced pressure, it creates a drag. Newer aircraft are generally made with consideration to this by fairing parts along the fuselage, teardrop, so that turbulence and form drag is reduced. Total lift must overcome the total weight of the aircraft, which is comprised of the actual weight and the taildown force used to control the aircraft's pitch attitude. Thrust must overcome total drag in order to provide forward speed with which to produce lift. Understanding how the aircraft's relationship between these elements and the environment provide proper interpretation of the aircraft's instruments. Newton's first law, the law of inertia. Newton's first law of motion is the law of inertia. It states that a body at rest will remain at rest, and a body in motion will remain in motion, at the same speed and in the same direction until affected by an outside force. The force with which a body offers resistance to change is called the force of inertia. Two outside forces are always present on an aircraft in flight: gravity and drag. The pilot uses pitch and thrust controls to counter or change these forces to maintain the desired flight path. If a pilot reduces power while in straight-hand level flight, the aircraft will slow due to drag. However, as the aircraft slows, there is a reduction of lift, which causes the aircraft to begin a descent due to gravity. Figure 4.4. Newton's second law, the law of momentum. Newton's second law of motion is the law of momentum, which states that a body will accelerate in the same direction as the force acting upon that body, and the acceleration will be directly proportional to the net force and inversely proportional to the mass of the body. Acceleration refers either to an increase or decrease in velocity, although deceleration is commonly used to indicate a decrease. This law governs the aircraft's ability to change flight path and speed, which are controlled by attitude, both pitch and bank, and thrust inputs. Speeding up, slowing down, entering climbs or descents, and turning are examples of accelerations that the pilot controls in everyday flight. Figure 4.5. Newton's third law, the law of reaction. Newton's third law of motion is the law of reaction, which states that for every action there is an equal and opposite reaction. As shown in Figure 4.6. The action of the jet engine's thrust or the pull of the propeller lead to the reaction of the aircraft's forward motion. This law is also responsible for a portion of the lift that is produced by a wing, from the downward deflection of the airflow around it. This downward force of the relative wind results in an equal but opposite, upward, lifting force created by the airflow over the wing. Figure 4.6. Atmosphere. The atmosphere is the envelope of air which surrounds the Earth. A given volume of dry air contains about 78% nitrogen, 21% oxygen, and about 1% other gases such as argon, carbon dioxide, and others to a lesser degree. End of page 4-4. Although seemingly light, air does have weight, and a 1 square inch column of the atmosphere at sea level weighs approximately 14.7 pounds. About 1/2 of the air by weight is within the first 18,000 feet. The remainder of the air is spread over a vertical distance in excess of 1,000 miles. Air density is a result of the relationship between temperature and pressure. Air density is inversely related to temperature and directly related to pressure. For a constant pressure to be maintained as temperature increases, density must decrease, and vice versa. For a constant temperature to be maintained as pressure increases, density must increase, and vice versa. These relationships provide a basis for understanding instrument indications and aircraft performance. Layers of the atmosphere. There are several layers to the atmosphere, with the troposphere being closest to the Earth's surface, extending to about 60,000 feet at the equator. Following is the stratosphere, mesosphere, ionosphere, thermosphere, and finally the exosphere. The tropopause is the thin layer between the troposphere and the stratosphere. It varies in both thickness and altitude, but is generally defined where the standard lapse, generally accepted at 2 degrees Celsius per 1,000 feet, decreases significantly, usually down to 1 degree Celsius or less. International Standard Atmosphere, ISA. The International Civil Aviation Organization, ICAO, established the ICAO Standard Atmosphere as a way of creating an international standard for reference and performance computations. Instrument indications and aircraft performance specifications are derived using this standard as a reference. Because the standard atmosphere is a derived set of conditions that rarely exist in reality, pilots need to understand how deviations from the standard affect both instrument indications and aircraft performance. In the standard atmosphere, sea level pressure is 29.92 inches of mercury, Hg, and the temperature is 15 degrees Celsius 59 degrees Fahrenheit. The standard lapse rate for pressure is approximately a 1 Hg decrease per 1,000 feet increase in altitude. The standard lapse rate for temperature is a 2 degrees Celsius 3.6 degrees Fahrenheit decrease per 1,000 feet increase, up to the top of the stratosphere. Since all aircraft performance is compared and evaluated in the environment of the standard atmosphere, all aircraft performance instrumentation is calibrated for the standard atmosphere. Because the actual operating conditions rarely, if ever, fit the standard atmosphere, certain corrections must apply to the instrumentation and aircraft performance. For instance, at 10,000 ISA predicts that the air pressure should be 19.92 Hg, 29.92 Hg, 10 Hg equals 19.92 Hg, and the outside temperature at -5 degrees Celsius, 15 to 20 degrees Celsius. If the temperature or the pressure is different than the International Standard Atmosphere, ISA, prediction and adjustment must be made to performance predictions and various instrument indications. Pressure altitude. Pressure altitude is the height above the standard datum plane, SDP. The aircraft altimeter is essentially a sensitive barometer calibrated to indicate altitude in the standard atmosphere. If the altimeter is set for 29.92 Hg SDP, the altitude indicated is the pressure altitude, that altitude in the standard atmosphere corresponding to the sensed pressure. The SDP is a theoretical level where the pressure of the atmosphere is 29.92 Hg and the weight of air is 14.7 psi. As atmospheric pressure changes, the SDP may be below, at, or above sea level. Pressure altitude is important as a basis for determining aircraft performance, as well as for assigning flight levels to aircraft operating at or above 18,000 feet. The pressure altitude can be determined by either of two methods. 1. By setting the barometric scale of the altimeter to 29.92 Hg and reading the indicated altitude, or 2. By applying a correction factor to the indicated altitude according to the reported altimeter setting. Density altitude. Density altitude is pressure altitude corrected for non-standard temperature. As the density of the air increases, lower density altitude, aircraft performance increases. Conversely, as air density decreases, higher density altitude, aircraft performance decreases. A decrease in air density means a high density altitude, an increase in air density means a lower density altitude. Density altitude is used in calculating aircraft performance. Under standard atmospheric conditions, air at each level in the atmosphere has a specific density. Under standard conditions, pressure altitude and density altitude identify the same level. Density altitude, then, is the vertical distance above sea level in the standard atmosphere at which a given density is to be found. It can be computed using a Koch chart or a flight computer with a density altitude function. Figure 4, 7. End of page 4 to 5. If a chart is not available, the density altitude can be estimated by adding 120 feet for every degree Celsius above the ISA. For example, at 3,000 feet PA, the ISA prediction is 9 degrees Celsius, 15 degrees Celsius, lapse rate of 2 degrees Celsius per 1,000 feet x3 is equal to 6 degrees C. However, if the actual temperature is 20 degrees Celsius, 11 degrees Celsius more than that predicted by ISA, then the difference of 11 degrees Celsius is multiplied by 120 feet equaling 1,320. Adding this figure to the original 3,000 feet provides a density altitude of 4,320 feet, 3,000 feet plus 1,320 feet. Lift. Lift always acts in a direction perpendicular to the relative wind and to the lateral axis of the aircraft. The fact that lift is referenced to the wing, not to the Earth's surface, is the source of many errors in learning flight control. Lift is not always up. Its direction relative to the Earth's surface changes as the pilot maneuvers the aircraft. The magnitude of the force of lift is directly proportional to the density of the air, the area of the wings, and the airspeed. It also depends upon the type of wing and the AOA. Lift increases with an increase in AOA up to the stalling angle, at which point it decreases with any further increase in AOA. In conventional aircraft, lift is therefore controlled by varying the AOA in speed. Pitch/power relationship. An examination of Figure 4.8 illustrates the relationship between pitch and power while controlling flight path and airspeed. In order to maintain a constant lift, as airspeed is reduced, pitch must be increased. The pilot controls pitch through the elevators, which control the AOA. When back pressure is applied on the elevator control, the tail lowers and the nose rises, thus increasing the wing's AOA and lift. Under most conditions, the elevator is placing downward pressure on the tail. This pressure requires energy that is taken from aircraft performance, speed. Therefore, when the CG is closer to the aft portion of the aircraft, the elevator downward forces are less. This results in less energy used for downward forces, in turn resulting in more energy applied to aircraft performance. Thrust is controlled by using the throttle to establish or maintain desired airspeeds. The most precise method of controlling flight path is to use pitch control while simultaneously using power, thrust, to control airspeed. In order to maintain a constant lift, a change in pitch requires a change in power, and vice versa. If the pilot wants the aircraft to accelerate while maintaining altitude, thrust must be increased to overcome drag. As the aircraft speeds up, lift is increased. To prevent gaining altitude, the pitch angle must be lowered to reduce the AOA and maintain altitude. To decelerate while maintaining altitude, thrust must be decreased to less than the value of drag. As the aircraft slows down, lift is reduced. To prevent losing altitude, the pitch angle must be increased in order to increase the AOA and maintain altitude. Drag curves. When induced drag and parasite drag are plotted on a graph, the total drag on the aircraft appears in the form of a drag curve. Graph A of Figure 4.9 shows a curve based on thrust versus drag, which is primarily used for jet aircraft. Graph B of Figure 4.9 is based on power versus drag, and it is used for propeller-driven aircraft. This chapter focuses on power versus drag charts for propeller-driven aircraft. End of page 4 to 6. Chapter 4 Part 2 is coming soon.